Hello, this is a video on how to calculate Avogadro's hypothesis gas problems. Now, if you have already watched a previous gas law or any gas problem video from me, then you can fast forward through this short little part about how to calculate, how to set up a gas problem. So if you haven't, you should have printed this out, and you should have looked at what another video I call the overall gas calculations, where I explain um, how how to calculate gas problems. There are several different types of gas problems, and in the video I kind of explain what questions to ask yourself so that you get to the right equation to use in your gas problem. And there are generally two questions you ask yourself, and this is a handout explaining the steps you need to follow for any gas problem. The first question you ask yourself is what I call how many conditions you have in a gas problem. You look at the problem and you read what the problem says, and there are either you're doing something to the gas or you're simply describing the gas. If you're doing something to the gas, you actually have what I call a two-condition problem. The first condition being the information about what originally the gas was, what condition they're in. So you have the initials, which I call 1, which will be the subscript in all the variables. So you can define what the gas is, P, V, N, and T. And then you do something to the gas, cool it, compress it, expand it, leaks, and then you have the new condition, which will have subscripts 2 in it. Okay, and you can usually tell by seeing action verbs. So if it's a two-condition question, you're going to ask another question. If it's simply you're describing the gas, and that's considered a one-condition problem. So our Avogadro's hypothesis is a two-condition question. And with two-condition questions, you have to ask a second question to come to the right mathematical relationship. And that is, how many things are being held constant? Because you have 4 variables. And for this one, Avogadro's hypothesis, and the 3 other gas laws, you're actually holding 2 variables or parameters constant, and then 2 are varying. Okay? From that, you're going to be able to come up with the correct mathematical relationship. Now, so for Avogadro's hypothesis, what's being held constant is temperature and pressure, and you're varying the number of moles in volume. Now, in the steps below here, the next one is write down what you know and what you're looking for, and then the next one is determine the correct mathematical relationship. You can do either one of these before the other, but you have to do both of them before you do anything else. So, so that, and then once you do, you plug your information into your mathematical relationship, and then you do math, and then you finish off by having the right units, right number of significant figures, and things like that. So with Avogadro's hypothesis, I declared all my variables, which I'll talk about in a little second, but I want to spend a couple seconds explaining to you how I get this equation. Okay? With Avogadro's hypothesis, it's the number of moles in volume are related to each other. So how are they related? Well, by now you should have done a gas law demonstration, you should have read something in the book, and you should know what the rule for Avogadro hypothesis is. Using my little analogy of a room with students in it and the students are the gas particles, temperature being how fast they're walking, pressure is the total number of hits on the wall in a given time, volume is the size of the room, and the number of students is n. So for Avogadro's hypothesis, you keep temperature, so how fast they're walking, and P, the number of total hits on the wall, constant. So if I increase the number of particles in the room, and I don't change how fast they're walking, and I can't change how many hits on the wall. If I increase the number of particles and I keep the number of hits constant, do I have to expand the room or contract the room? Make the room bigger or smaller? And of course, to keep the number of overall hits on the wall constant, where I increase the number of particles or students, I would have to increase the size of the room or the volume of the room, which tells you that the number of moles is directly proportional to the volume. So it's a direct proportion. And as you know, with a direct proportion, and to set up your equation, mathematical equation, with both variables on the same side of the equal sign, that if they're directly proportional, then one's on the top, one's in the numerator, and then one's in the denominator. So N1 and V1 need to be on opposite sides of the line, as in if one's in the numerator, the other one is in the denominator, or vice versa. And that's why, if you look at here, that's why V1's on the top and N1's on the bottom. So why do and this is the only way I'm going to allow you to write the equation. You can't put the ratio of the variables in condition 1 equal to the ratio of the conditions in 2. I want you to write it this way instead. And the reason is, if you look at the equation, it's very simple to set up. So V2, how do I know it's V2? Because you're looking for V2, it tells you that. Well, V2 better be V1 times the ratio of the moles and how the moles are changing. So really, the only thing you have to know is if V1's on the top, you need to know where you put N1. Well, since they're directly proportional, if V1's on the top, N1 must be on the bottom. And then you know exactly where N2 is because it's the only spot left that there isn't any subscript. So therefore, that's the relationship. And this is this math equation is a lot better because really you can take a look at your ratio of the moles to get an estimate of the value of V2 versus V1. Okay, so that's the equation you're going to use. So you set up your variables, and again, these are kind of like math equations. So usually in one sentence gives you the information about one condition. So it says the gas volume is V1 is equal to 345 milliliters. Inside there you have 2.05 moles. Then it says if the container leaks, here's your action verb, leaking. There is now 1.45 moles, and what's new volume? So these are N2s. So therefore now you plug it in. Your moles are going to cancel, okay? And it's in milliliters, and they ask for milliliters. So you get your answer in milliliters, and then you get the number of significant figures. If they said what's the new volume in liters, you could do that one or two ways. You could have changed it right here into liters and plugged it in, or you could go and get the answer, of course, with one more significant figure in milliliters and change it into liters and then put it into one significant figure. Okay. Either way, it's totally appropriate. Okay. So that's how you do a calculation for Avogadro's hypothesis.